Olá, saudações virtuais a todos. Na qualidade de docente da UFPB e membro da comissão organizadora do CTRL-E 2020, que tem como tema Educação do Futuro, Tecnologias e Pessoas para Transformar o Mundo, eu tenho a honra de convidar o professor Tim Bell, que irá proferir a palestra O Valor de Ensinar sobre Tecnologia, bem como de ensinar com tecnologia, ou The Value of Teaching About Technology as well as Teaching with Technology. O professor Tim Bell é professor no Departamento de Ciência da Computação e Engenharia de Software da University of Canterbury, Nova Zelândia. O seu projeto Computer Science Unplugged, ou Computação Desplugada, tem sido amplamente utilizado internacionalmente e foi traduzido para mais de 25 idiomas. Tim recebeu muitos prêmios pelo seu trabalho na educação em computação, incluindo o prêmio de 2018 intitulado ACM SIG CSE's Outstanding Contribution to Computer Science Education. Desde 2008, ele participa ativamente do projeto e desenvolvimento da abordagem para o ensino de tecnologias digitais nas escolas da Nova Zelândia. Ele também toca instrumentos com teclas em preto e branco. Passo a palavra ao professor Tim Bell. Welcome to CTRL-E, Professor Tim Bell.
Kia ora koutou. My name is Tim Bell. I'm from the University of Canterbury in Christchurch, New Zealand, and it's really good to be with you today. The subject of my talk is the value of teaching about technology as well as teaching with technology. Now, it's really useful to teach with technology. We use it for all sorts of things, and the internet is a great way for students to access information. But it's also really important that we teach about technology. But let me start with a story. My wife is a music teacher, and one of the things that happens at the end of each year, our school year finishes just before Christmas, is that all her rock bands and orchestra and jazz band and so on record music for a compact disc. And she has to give these CDs to the students because, of course, they leave school, she finishes organising them, and she has to get them out to the students. So every December she has this pile of CDs and they all get put in cases, and then they have to be taken around about 30 different students' houses. And it's a tradition that we have. We drop them off each Christmas, and it's kind of fun because you're visiting people just before Christmas. But one year, as we're about to take off, she said, hey, I've just bought a new app that will tell us the shortest way to deliver these CDs to all of the different houses. Now, let's just step aside for a minute and look at some computer science about this. So I have this app here that solves the problem. It's a very old problem in computer science. It's called the travelling salesperson problem. And we imagine that someone has to travel around, in this case, 7 different cities, and they want to find the shortest way to visit every single city just once. Now, this app here, if I start it going, it's trying out every possible way every possible order that we might visit these 7 cities. And on the right-hand side, it's recording what is the best one so far. So already it's found one that's 16.41 kilometres long, but it's going to take about half a minute to try out every possibility for these 7 cities. Now you can see that this is exactly the same problem that my wife's app would solve. It was trying out all the ways that we could visit the students' houses, and it would give us the best one, and that's good. That will save fuel, it will save time, it will be good for the environment, and here we have it. This is on the right-hand side, the best possible way that we could have visited those 7 houses. It's a very common problem. We're interested in this because couriers need to be able to drop things off efficiently, deliveries need to happen efficiently, and so on. Now, my app is trying out every possible way of visiting these 7 places. And a question I like to ask students is, if trying out every possibility for 7 of them takes half a minute, how long will it take to visit 14, or at least to try out every possibility for 14? And if you're a teacher, you might be aware that many students will say, well, obviously it'll take twice as long. Now, which is about a minute. But in fact, if I increase this up to 14 places, down the bottom here, it says that it's going to take 9 years, 10 months, 14 days, 10 hours, 24 minutes to try out every possible way to visit them. So I'll get this started. And it really will take that long because there are just that many possibilities. Every time we add one place that needs to be visited, it multiplies the number of things to try out. So we have here an exponential amount of time that will be needed. Now, people say that computers are getting exponentially faster, but the trouble is, of course, every time the computer gets, say, 10 times as fast, it probably only helps us to calculate this for one more city. So it doesn't actually help us a lot when your problems are exponential in nature. Now, believe it or not, there are faster algorithms, faster ways to solve this problem, but they are all exponential. All the ones that give us the optimal answer, they guarantee to give the best answer, take an exponential amount of time. In many decades of research, people haven't found any that are faster than exponential time. We have some that don't guarantee to give us the best route, that's okay, but in general, it's going to take way too long. 9 years is not worth it. No one's going to wait 9 years to save a little bit of fuel or a little bit of time traveling. And it gets worse, in fact. If I crank this up, so let's add a few more cities, we'll make it 3 times as big, and I'll have 21 cities. And down here we see that it's going to take 3,800 million years and 9 months, 21 days and 6 hours, I'll get that started, to do this calculation. And so no matter how fast the computer is, even if the computer was 1,000,000 times faster, it's still going to take thousands of years to solve the problem by trying out every possibility. Now, getting back to us sitting in the car about to deliver these CDs to the students, what happened is that my wife said, well, I've actually just found an app that solves this problem, and she paid $4.99 for it, so it wasn't a cheap app, but what you could do is put in all of the places you wanted to visit and it would work out the shortest route. It was called Eco Maps. And here's a picture of it. And she typed in about 5 houses and pressed the go button, and it figured out the shortest way to visit 5 houses. So that looked very promising. Now I'm sitting there thinking, I'm a bit suspicious. I don't know if this is going to work, but I just sort of played along. And so she typed in 30 street addresses, all the places that we're going to visit, and pressed the go button. And it just sat there. And we waited a couple of minutes and it still was sitting there. And I was thinking, exponential amount of time. This could be a very long time. And so I suggested, well, why don't we just go to the nearest house first? It might not be the optimal one to visit first, but let's go there anyway, and we'll drop off that CD and then we'll carry on to the next house. And that was fine. And then as we left that house, we went to another nearby house. She was looking at her phone, and guess what happened? The battery went flat. The system had used so much power, it had been doing so much calculation that it flattened her battery on her phone. Now, when you're with a music teacher on Christmas Eve, a flat battery in a phone is not a happy situation. But that's what happens when we use a bad algorithm, when we use the wrong method for doing things. It uses more power than it needs to. Now, it may not matter all that much if your mobile phone goes flat occasionally, but it does matter if you're a very big company running lots of searches or running lots of video feeds or anything like that. And if you're using slow algorithms, you're using a lot more power, a lot more computing, a lot more resources than you need to. So I thought this EcoMaps app was so interesting that I bought my own copy as well. And when I went to buy it, I saw all of the reviews for it, and it had terrible reviews. People were saying that it doesn't work, it's very slow, it runs the battery flat on their phone and so on. They were very unhappy customers, and they'd spent quite a bit of money on it. And after a while, this sign appeared on the website. It said, "Please note, the speed of this application is limited by technology." Well, it's not really limited by technology, it's limited by the understanding of the person who developed it. Now, the psychologist Albert Bandura once said that everyday life is increasingly regulated by complex technologies that most people neither understand nor believe they can do much to influence. The complex technologies are all around us. We have mobile phones and tablets and laptops, but also things that are built into our buildings, alarms and things that control lights. All sorts of technologies are influencing our life. And Bandura pointed out that a lot of people don't understand them. They don't know how they work. Often people talk about they have invented some artificial intelligence. They have invented something that has computer vision built in. They have invented a car that can drive itself. But not being able to understand it and leaving it to they is not a great idea. And even worse, of course, people don't think that they can influence it. Now, we want our students to not feel like that because they, the people that are doing this, are actually going to be your students one day. The people who are in your classrooms are going to be the people who invent and build the new technologies that we're going to use. And so they have to understand it, and more importantly, they have to feel that they could influence it if they wanted to. Now, often we hear about the idea of coding and that it becomes very trendy, and this is understandable because if you can write computer code, then it means you can build complex technologies, and it is very empowering. But there's a lot more to understanding the technology than just being able to code. The person who wrote the program that my wife bought for $4.99, did I mention that, is someone who could code, but they didn't understand all of the ideas around it. And those broader ideas are sometimes referred to as computer science, but recently it's often referred to as computational thinking, thinking about programs, thinking about how to write them, but also thinking about how to improve them, how to make them go fast, how to make them easy to use. And this term was brought to fore by Professor Jeanette Wing, who said that, or who she defined it as, computational thinking is thinking like a computer scientist. There are a few other definitions around as well, but this one's interesting because it's basically saying we want our students to develop computational thinking because we want them to understand computer science. We want them to be able to think like a computer scientist does when they solve a problem. Of course, that really raises the question, what is a computer scientist and how does a computer scientist think? Well, I thought I'd illustrate that with an app that I use quite regularly, and it's probably the most popular one in the world, and it's a website called Google that we use for searching. Now, when you look at it, the Google website is actually just one text box and these two buttons here. And in fact, hardly anyone presses either of the buttons. They just type into the text box and press return. So a very simple interface, and yet what it does is very powerful. For example, the project that I'm involved in is called CS Unplugged, and I'll talk more about that in a minute. But if I start to type C for CS Unplugged, it's actually having a guess at what I might be interested in starting with C. I'm not actually interested in those, but I'll type CS. And by the time I type that, it's saying, oh, maybe CS Unplugged is the thing you're interested in. And it's also found a couple of other things I'm interested in. The writer C.S. Lewis, and there's a few other things that begin with CS. As soon as I type U, it's really starting to narrow in on things I'm interested in. Interestingly, down here we have things like a C sus chord, which happens to start with CSU. I'm involved in music, and so somehow it's profiled me and said, well, maybe you're interested in the musical application, but I'm more interested in this first one. So a very simple view of this is that we have a text box and two buttons, and a programmer has to write a computer program that reads in some text in the box and goes through a whole lot of web pages looking for a match for it. Not too hard a program to write, but it would run very slowly if it went through every web page in the world looking for your text. It would probably take weeks and weeks to give a result, and no one would use that search engine. Now, that's what computer programming is, though. It's about just making software. It does what I asked. You type something in, it will search for it. But of course, we're interested in way more than that. And so when we think about computer science, what we're interested in is making software that is fast. We also want it to be very efficient so that it doesn't waste a lot of computing power. We want it to be reliable. We want it so the reliability is really important because people don't like using software that breaks down or doesn't always give you the right answer. It has to be very secure. When I'm doing a search, it knows everything that I've searched for in the past, and I don't really want other people to find out what I've been searching for. I don't mind too much, but it's not great for privacy. So their software has to be secure, and any system that people develop, security is a really big deal. It has to be usable. It has to be easy to use. I don't think there is an instruction manual for Google searches, and if there is, I don't think many people read it. And usability is where it's a lot easier for people just to start using the software. That doesn't just come naturally. There's probably lots of software you've used that's difficult to use. Software also needs to be scalable, that if you suddenly have lots of people using your site, you want it to be able to scale up and not just suddenly go really slowly. And it might even be a bit intelligent. For example, it was predicting what I was going to type. Here I've typed in "why are computer scientists?" and it's predicted a whole lot of questions that I might be asking about computer science. So that's the difference between programming and computer science. It's not just making the program work, but it's making it work in a way that people really like it. And that's why I know that that app that my wife bought for $4.99 was probably written by a programmer, but not someone who had that broader understanding of computer science or computational thinking. So the topic that we are introducing in schools is a lot broader than just coding. It's getting students thinking about all of these issues. So I've already talked about how it's good for students to learn with computers, but important for them to learn about computers, about how they work. Now you would think that normally you would learn about computers with computers, that you would use a computer to learn about the computer. And that is a very important way to learn about computers. But I've been involved in a project where a lot of the time is spent learning about computers, but without computers. And we call it Computer Science Unplugged. And it's a really popular way to get students engaged with the idea of computing. Now, to get started off, I'm going to show you the idea of how binary representation works on computers. Now, the word binary often scares people when they see it. It sounds like a very mysterious thing, but everything that's stored on a computer uses this binary representation. Now, rather than just teach it myself, let's have a look at a video of one of my colleagues, Joanne, who is working with some students and teaching them about how to represent numbers using just yes and no, 0 and 1.
We're going to look at how to send information just using yes or no. That sounds pretty cool, eh? That's pretty cool, eh?
Yeah.
Yeah. First, I'd like you to turn over this card, please. How many dots does that show?
1,
1, you're right. Turn over this card. 2, great. Oh, how many dots do you think will be under this card?
3,
3.
3,
3. Let's have a look. Oh, fantastic. You might see a little bit of a pattern. Can you work out how many dots will be shown on this card?
6, 8. Right. Oh, I get it now. I've been can I use this one?
Oh,
Oh, I get it.
you get it. So what do you think this one's going to show?
16.
Oh, flip it over. Fantastic. Well done. You're pretty smart.
I figured out the trick.
Now we want to show 9 dots. When we're using these cards, there's just one rule, okay? We either had them showing up with all the dots showing or down with no dots showing, okay?
I already know the answer.
So do we want this card?
No.
Cool.
Yes. No.
Do we need this one? No. Do we need this one? Yes. Let's see if you can do the number 11.
No. Yes.
This one?
No.
This one?
Yes. Yes.
So we've shown 11 dots just by saying no, yes.
No. Yes. Yes.
That's pretty cool, isn't it? I'm going to tell you what month I was born in just by saying yes or no. Okay. No. No. Yes. Yes. No. What month was I born in?
6.
6. What month do you think that might be?
June.
You're absolutely right. Well done. How did you get June?
Because my brother's birthday is on June as well. July.
Nearly. How did you work that out?
I just guessed.
January, February.
March, April, May, June.
How did you work that out?
Because I know that because since there's 12 months in the year, I know that 4 plus 2 is 6,
And it's either June or July.
June.
I said no, no, yes, yes, no, and you worked out that I was sending you the information of the 6th month, which is June.
Okay.
Right. If you were wanting to use these dots, do you think you'd be able to tell me some letters using just dots?
Because with the alphabet, like A is 1 and then B 2.
The letters become numbers and you have to use the numbers to create a certain letter and then use the letters to create words.
How many dots do you think we should show for the letter A?
1.
1, that's a good idea. And how many dots would we show for the letter B?
2.
Yep, and for C?
3.
Yep, and 4? That's 4 is not a letter of the alphabet. Right. Do you think we could say that A was 1 dot?
No.
No? Could we say A was 1 dot and then B's 2 dots and then C would be 3 dots? Do you think we could do that?
No.
Shall we have a go at it anyway?
Okay.
So I'm going to say no. Turn the card over. Yes. No. 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 What's the first letter of my message?
H. A, B, C, D, E, F, G, H.
You're right. How did you work that out?
I counted on my fingers.
The first 4 letters of the alphabet is D, and then if you just carry on, you get to H. I just went to A, B, C, D, E, F, G, H.
Here comes the second letter of my message. No. Yes. No. No. Yes.
B, C, D. I.
How did you know it was I?
I just counted these dots in letters in my head.
What's my message?
Hi. Hi.
Hi. Good job. Do a high five? Yeah.
So those students have learned a lot about how data can be represented just storing yes and no, zeros and ones. And eventually they could explore how this is happening on a computer, how computers store numbers and letters and pictures and all sorts of things. Now, why would we care about that? Well, we go back to that quote where we talk about how students understand how these things work. If everything that we store on a computer uses these binary numbers, then it helps us to understand what is happening underneath. For example, those binary digits, which are called bits, appear all over the place. We have 8-bit ASCII codes for characters, which are limited. They can't represent every language that people might want to use, so we have to move to 16-bit codes and so on. We have 16-bit computers or 32-bit computers or even 64-bit computers. What does that mean? Color, it might be 24-bit color or a different sort. Encryption, maybe you have 256-bit encryption. How good is that? What is a bit? And so understanding these binary digits will help students to understand some of the things that are critical to how our computers work. I'll do something a little bit different with how we store information on a computer. So let's take a photo. I have here a picture of a duck, and let's take a photo of it. And I have an app here, and we'll provide the link for this one and the other apps that I've been demonstrating. In this app, I can zoom in on the picture, and as I zoom in, after a while, you start to see that it's made up of lots of tiny little squares. Those squares you're probably familiar with, they're called pixels, which stands for picture element. Now, each of the pixels is, if we zoom in even more, each of these squares is a single color, but I'll just carry on zooming in on this orange one here. As we go in far enough in this app, we can see that these colors are represented by some numbers. So this orange here is represented by the numbers 255, 133, and 62. They're RGB. Now, what does RGB stand for? Well, a lot of people might know that this is red, green, and blue. But why do we represent a color using a mixture of red, green, and blue? Well, it turns out that we can mix together these colors and get any colour that we want. So, for example, I have a mixer here that at the moment I have 0 red, 0 green and 0 blue, and I could turn up the blue a little bit and you see the colour on the left becomes quite blue, and maybe I'll add some green to it, and as I mix them together I get this nice turquoise colour, and if I have lots of green and then it's a bluey green colour and so on. Now I can actually get all sorts of colours by mixing together those 3 colours, red, green and blue. They're called the primary colours. By the way, if I mix red and green together, some of you may not know what that produces. It actually produces the colour yellow when you have enough of it. So if I go back to my pixels, if I take this one in the top left hand corner, which is 255, 133 and 62, I can put in the 255, 133, just get that right, and the 62, I'll just type that one in to get it accurate, and I've reproduced the colour. So going back to the pixels, if you were to read out all of these numbers to me, then I could reproduce every colour in this image. And in actual fact, if I turn off the colours there, that's what it really looks like to the computer. It's just a whole lot of numbers. In fact, this is a digital photograph. Digital photographs are just a whole lot of numbers. That's what digital means. And in fact, when we talk about digital technology, this is the whole point. The digits are numbers. And how are those numbers stored? Well, they're represented using binary digits. And so those binary digits are actually the thing that makes digital devices digital. Starting to get the picture that we're starting to understand what's going on behind the scenes. And by the way, if I gave you all those numbers, then you could colour them in, work out the colour of every pixel. And of course, pixels are really small, so if they were really small, you'd have reproduced the original picture. That's how we send pictures on the internet. That's how we store them on cameras and on computers. It's just a whole lot of numbers. But I still haven't quite answered the question, why do we choose red, green and blue? Well, actually, we didn't choose it. It's how we're made. The eyes have what's called cone cells in them, and they detect colour. And the cells that are in your eye are either red, green or blue. They're able to detect those colours. Well, actually, for most of us, they're those colours. Some people don't have red-green working so well, and so they're red-green colourblind. But in general, those are the 3 colours that we detect. So everything that you see is being seen through as sensing red, green and blue. Which now reminds us that the system wasn't devised using red, green and blue because some technical person thought of it. It's devised because it's designed for people. And that's one of the themes I really want to bring out today too, is that computer systems are designed for people. And if they're not, then people don't like to use them. And if nothing else, if we are teaching our students how to influence computer systems, we want them to influence them to be better for people. When we say better for people, so that people can experience them in a way that's easier to use, so that they're fast to use, so that they're helpful, so that they don't do any harm, and they help people, make good decisions and so on. So the people who do really well at designing these systems are the people who are focused on other people. And often in culture, in popular culture, the image of someone who's good at computing is not someone who thinks about other people or likes even being with other people, but those are the people who produce the best software. So that's why we want our students to have more of an understanding and even the ability to think that they can influence this technology. So let's look at a different application of digital technology. In New Zealand, QR codes are used quite a bit for tracking where people have been because of the COVID-19 outbreak. Now, these are on shops and in buildings, and people hold up their cell phone, and when they scan the code, it records where they are. Now, when you look at a QR code, the binary digits, the zeros and ones, are quite obvious. We've got these black and white squares. And that's all that's happening when you scan one, is it's actually reading in those binary digits. But if you look at the one on the left there, it's in a cafe and it has a bit of light shining on it. And so some of the black ones look a wee bit white. And then the one on the right, it's been put on a window, but the window has this grill in it and it's added some black lines to it. So the worry is that maybe when you scan it, you get the wrong information. Well, I've created this QR code here, which actually we're going to have a go at scanning and seeing how things may or may not go wrong. So here's a piece of paper with the QR code on it, and I'm holding my phone up to it, and it scans it, and there we are. It's the Computer Science Unplugged website. Now, that's all fine, but let's change one of those binary digits, one of those zeros and ones. So I've chosen this one here, and I'm going to change it from white to black. Now, you'd think when I scan it now, it will read in a different website. Maybe one of the characters will change because it is different data, but actually it's exactly the same. Changing that one binary digit didn't seem to matter. Let's try changing a few of them and see if that gives us a different website. Now, this is a great exercise to do. Of course, when it happens in real life, it's a worry because it might send you to the wrong place. But no, it's still scanning it okay. It seems that a lot of these binary digits aren't essential. But which ones? Did I happen to just colour in the ones that don't matter? How is it coping with that? Let's have another look. And I'll just point out that this is something that all data has to be concerned about. It can be changed accidentally. It's still scanning okay. Let's change it a little bit more. We'll change a few more of the zeros to ones or ones to zeros and see if it scans to something different this time. So here we go with a scan, and this time it won't scan. It's not giving me the wrong information. It's just saying that there's something wrong with this QR code and I'm not going to scan it for you. I'm not going to give you a value from it. Now, that's really important because so much of our data is digital that if any of those binary digits get changed, we'll be working with wrong data. Finance will be wrong. Students' grades will be wrong. And so what's happening here, it's really important that we either get our data, and even if there's small changes to it, we still get the original data, or at least the system tells us that the data's been corrupted. How does that work? Well, I'm going to get my colleague Joanne to demonstrate this idea to some children. Let's follow along.
I need 2 people to set up a grid for me, please. It'll be 5 by 5, okay? Oh, okay. You too, that would be great. Cool. All right, so it's going to do it totally random, some black and some white. That's it, good. All right, I think we're done. I'll have those cards back. Fantastic, we've got 5 rows of 5, haven't we? Good job. Right, now I've been, good job. I've been doing this for a while, so I'm going to add some more to make it a little bit harder just for me. Otherwise I get a bit bored sometimes. There we go. There we go. Right, now I'm going to turn away and I'd like you please, while I've got my eyes covered and I've turned away, I'd like you to turn over 1 card please, okay? So the rest of you can see which card it is, but I'm not going to see which card it is. Okay. Is it flipped?
Not yet. Okay, now it has.
Is it flipped now? Okay, yeah, I'm turning around. Right, now, if a computer got this information, it wouldn't be able to use it, it would be wrong. So the computer would know it had to turn that bit over.
How did you know?
What? How do you think I knew?
You picked.
I picked? I didn't pick, I was sitting with my background, you guys picked.
No, so I was staring at it.
I was looking that way. I had my eyes covered.
Can you see through? Can the glasses be used as a mirror? See?
Mine are just very boring glasses. Hang on, let's do it again, just to make sure I wasn't cheating. This time I'll cover up the eyes and the back of my head as well. Okay? Here we go. Right, this time I'd like you to turn the card over. Okay? Here we go. Is it flipped?
Yep.
Okay. All right. Which one use it? I will use my mighty powers. I think it was this one.
No. Oh, I know how you did that.
How did I do it?
You memorized all of the way they looked, and then you found which one looked different from the way before.
I would love to have a memory that good, but no. I'm going to tell you a secret. I'm going to let you know. Here we go. How many white cards are in this row?
2.
How many in this row?
4.
In this row?
2.
This one?
4.
This one?
4. 4.
Fantastic. Now we'll go this way. How many white cards in this row?
4.
This one?
4. 2. 4, 4, 2.
Fantastic. What do the numbers 4 and 2 have in common? Maybe 6 and
I'm
8.
pretty sure because they're a pattern.
They are a pattern. What is the pattern?
There's just 4s and 2s.
It is just 4s and 2s. And what's the same about 4s and 2s?
They
What's
are
this
both
for?
equal numbers.
Is equal the word not quite starts with E? I forgot.
Even.
Even. They're all even numbers, aren't they? So what happens if we turn one over?
It'll be odd.
You're exactly right. Did you guys set that up so that they were all even?
No.
No, because I added these ones, didn't I?
Yeah.
You guys set up the 5 by 5, didn't you?
Yeah.
And then I said it was to make it harder, but I was cheating, I was making it easier. You guys are going to help me to put them back now. So to make this one right, do we want black or white?
White.
Black. Why do we want black? You're right. Why do we
Because
want
then there'll be 2.
2 white ones? Because we
white
want to make it even numbers, don't we? What colour do we want one here?
White.
White. And here?
White. Black.
Black, because we're making it so we've got even number of whites, aren't we?
White. Black.
Hang on. White.
Black. White.
Make it even. There we go. Now we'll do this row here.
Oh, wait, are we going
It
down?
needs to be black. Going across now.
Oh.
And this row needs what to make it even?
White.
You've got the pattern.
White.
This one.
White.
Yep. And
Black.
this one. Black. Oh. And this
White.
one.
White.
White. Now this one. Are we going to look at this one or this one?
Both.
If we look at this one, what would we need? We need black and white to make this one even.
White.
We'd need white. And this one here, would we need black and white to make it even?
White.
White. So that's how I know that I've set it up right. If this one works for both that row and that row, then I've got it right. If I get here, and I need a black one for that one and a white one for this one, I've done it wrong. Now, who reckons they'd be able to do it? I'll help you to do it, but who reckons they'd be able to make it? Yeah? Yeah, okay. Here we go. So you need to turn around. Right, cover up your eyes and the eyes in the back of your head. Awesome. Can you please choose one, flip one card over? Good job. Right. Okay, turn around. Right. Is this row okay?
Yes.
Is this row okay?
Yes.
And this one?
Yes.
This one?
Yes. Yes. No.
Oh, we'll mark that one off then. Is this row okay?
Yes. 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 No. Oh. Yes. Yes.
Yes, yep.
No.
Oh, we'll mark that one off then. Okay, so we know that something's wrong in this row and something's wrong in this row. Which card do you think she flipped?
This one.
Is he right?
Yes.
Good job.
So the way that Joanne presented that was as a magic trick. And a lot of the things that happen in technology seem like magic. To some extent, they are. It's amazing what we can do with digital technology, but we don't want it to remain magic. That's part of what we're talking about. If it all seems magic, then it's pushing students out from understanding how it works. So we want them to understand the magic trick. Now, I want to see if you were following along, so I'm going to give you an exercise. Here are some students who have put down this magic trick, and by the way, it's called parity. Parity just means odd and even numbers. And what they've done here is they've made sure that there's an even number of black cards in every row, or an even number of white cards. It doesn't matter which way around it is. And also every column has an even number of black cards and an even number of white cards. But they've changed one of them. Now this grid is much bigger than the one you saw before. It's got 100 cards in it. And this data was generated by students on the other side of the world from you. But let's have a look and see if you can work out which card they flipped over on this grid. One of these cards is wrong. To make it a bit easier, I've put some numbers and letters across it. So have a look at it and see if you can work out which row is the one that has the incorrect card in it and which column is the one that has the incorrect card in it. Maybe pause the video, have a look at it, and then come back. Okay, so I hope you worked that out for yourself, but what you've hopefully realized is that if you go and look at column number 6, it has an odd number of white cards and an odd number of black cards in it. So one of those cards was flipped over. And then when we look at the columns, column G also has an odd number of black cards in it. So the card that they flipped over must be the one at the intersection. In other words, we've identified that that particular card there should be flipped over, and then all of the data would be correct. Now, this data, it could have been a message, it could have been storing a picture, it could have been a video, anything that was digital that's stored on a computer. But what we've done now is realized that it's possible that even if that data was corrupted or changed, we can put it right. Of course, the next question is, what if more than one card was flipped over? Is it possible to detect that there's an error? And if you can detect an error, can you fix it? And so these are all questions for students to explore. And it just opens up the whole way that this area of technology works. Now, the QR code that I was using before, I was colouring in lots of these binary digits and it would still correct it. And this particular system here, just so you know, it can only be used for correcting one error. So the QR codes use a much more sophisticated system, but it's the same basic idea. And the general principle is that we can find errors and we can often correct them when the data gets changed. So you may have noticed that we're learning about computers, but we're not really using the computer to do that. In fact, the examples I've given you have involved cards, maybe a pen, and a few other bits and pieces that are quite easily found in the classroom. This approach to engaging with computing is called Computer Science Unplugged, or just Unplugged for short. People often refer to it that way. And it involves having students being away from the computer and thinking about what's happening. We use constructivism, we get them to solve problems, we get them to think about it and explain what's going on. And it involves physical exercise, kinesthetic activity. The activities can be great in conjunction with using a computer, because I think often students think a little better when they're away from the computer, and when they get back to the computer, they seem to be able to do a lot better. Even if they're learning to program or something like that, doing the unplugged activities helps a lot. And there's a growing amount of research that supports that idea. One of the unplugged activities that's been very popular is one called parallel sorting networks. So I do want to share that with you. It is done by marking out this very simple pattern on the ground. Now, where this came from actually is a colleague of mine who also developed a lot of the unplugged activities, Michael Fellows, was giving a lecture just before he had to go and work with some children. And he wasn't sure what he'd do, but he'd been lecturing about parallel sorting networks to third-year university students. And he thought he'd try that with the children. It was a big hit, and it's become extremely popular. So let's have a look at a video of my colleague Tracy, who is going to be demonstrating it with some children.
So we've come outside today to learn a little bit more about how computers work, and what we have is, this is like a supercomputer made out of chalk, and I'm going to show you why in a moment. I need 6 volunteers. Oh, awesome. What I'm going to do is I'm going to give you a disc, and you need to go and stand on the circles from the far away one. So Riley, you go away over from that far away one. Robert, you go into the next one. Ellie, you go over to the next one. Koresh, can you go over there? Lewis, can you go into the last one? Okay, so I've got you guys here, and this is all about teamwork, and it's all about organising data. So you guys are the start of the data, you're coming in and you're all out of order. We've got the number 5, number 2, number 1, number 3, number 6 and number 4. And so before we start going into the supercomputer, all I need to teach you is this symbol here. What does this symbol here mean? What does it mean, Lewis?
Smaller and bigger.
Smaller than bigger. What's some other mathematical terms that we could use for smaller and bigger? Yep. Less than or greater than. Awesome. So what we have is the orange line is the less than, and the blue line is the greater than. So let's see how this works. Can you all take a step into the box? Can you say hi to the person next to you and give them a big smile? Not too cheesy. Now what you need to do is decide, have I got the bigger number or have I got the smaller number? And then the bigger number follows the blue line, the smaller number follows the orange line. Go. Now, you need to look around and check everyone's there, and then you need to say hi and give the person a big smile. Go. Now decide who's got the smaller, who's got the greater number. Do you guys know what to do? Do the next one. I didn't see anyone smiling and saying hello. Smile and say hello. Now make your decision. Go.
Hello.
Nice.
What number do you have? I have 4, so
Perfect. Cool, so I'm going to get you guys to turn and face me this way, and we're going to see what happened to our numbers. Can you turn and hold up your numbers, please? Oh, wow. Koresh, what number have you got? What number have you got, Lewis?
3, 4, 5, 6.
Okay, what just happened to our numbers? We put them into our supercomputer that's chalk, that's like a supercomputer, and we processed it, and what happened?
We came back in the right order.
Huh. Do you think that would work with everything?
Yes.
What kind of things could we sort in order, do you think? Yep.
Books,
We could sort books. What else?
letters,
Yes, what else?
bells,
Yes, what else?
notes, and a
Yes, what else? What about big numbers? Really big numbers. Could we do that? Yeah, cool.
Which one sounds lower and which one sounds higher? A lot. Sweet. Okay. Let's do it one at a time. So yep. Which one sounds lower? Yep. Let's try play it just once more to make sure. That sounds good. Let's hear it. Let's hear it one more time. Yep. Yep. Okay, keep going.
So what you might have noticed in the video is the children are getting some exercise, they're thinking. And one of the really big ideas in here is that a very simple component, two people comparing a value and deciding which way to go, is able to be put together into something much bigger. If you put it together in just the right way, you can achieve something quite impressive, in this case, sorting values into order. And that's the thing about computing, is what computers can do is actually very simple. They can compare values, they can store values, they can repeat things over and over, but there's just a few things like that that they can do. When you put them together in the right way, we get all the amazing things that we can do with computers. That's the power of computation. So working with a parallel sorting network gives students a little bit of an insight into that magic, where a very simple element can be put together to achieve something much bigger. Now, the other thing you may have noticed is that there was some integrated learning going on, and this is always good if we can integrate what we're learning about in computing with other subjects. So, for example, the students were comparing book titles, putting them in alphabetical order. Understanding the alphabet, understanding a sorted order of names is quite a big deal. It's actually quite hard work. Now, we've also done that with things like musical notes. Which note is the lower and the higher note? They go left and right. And you saw them doing it with bells, which is the lower pitch and the higher pitch. Anything that can be compared can be sorted with these sorting networks. So we've found that teachers are using them over and over because they can teach all sorts of different topics using this basic structure. At the same time, the students are getting used to an idea from computing that this very simple element can produce something quite powerful and that it can be applied to all sorts of topics. So I hope that's given you some insights into how we can teach about computers. Now, programming is important, but one of the ideas I hope you've picked up is that we don't write programs for computers, we write programs for people. That a program only means something if someone can use it, and it has to make the world a better place for us. It has to help people with their work and not get in the way. For example, if you've used a computer program, you might have had terrible error messages. This one here just says, Unspecified error. Sorry, an error has occurred. Please try again. And you probably know that whenever an error message says please try again, it's probably not going to help. And even students, when they write their computer programs, need to be aware of this, that they're writing for people in the way that they design them. Here's something from a quiz written by a student where they've said, "You're wrong." It's not a great interface. It might be correct to say that the answer is wrong, but there are better ways to communicate to people in the interface. So we want to make our students sensitive to the idea that the software is being developed for people. It has to be easy to use, it has to be fast, it has to be reliable, it has to be secure, all those things I talked about at the beginning. And to understand all of those aspects, then we can do all sorts of exercises, not necessarily on the computer even. We can use unplugged approaches. But in the end, I hope that if any of your students go on to develop programs, they won't write programs like the one that I talked about at the beginning that my wife bought, and it didn't do anything useful. So what is the purpose of teaching computer science? Well, we often hear about teaching students about coding, and coding is important. It's the thing that makes things happen on a computer. But we need to think about what we're coding. It's no good if you just write a program, but nobody wants to use it. So we do want to help them develop skills for coding and other aspects of computing. We also want them to develop a vocabulary so that when people talk about digital technology, when they talk about binary digits or error codes, that they can understand roughly what these things might be, because they do affect our everyday life. But we also want them to develop self-efficacy, the idea that maybe they could influence this, maybe they could write a program, maybe they could challenge the way that things are being done with technology. We're really interested in diversity because if products are developed by a group of people who are not diverse, they generally only suit that group, and we end up with way better software if it's developed by a diverse group of people. And in many countries, one group that's particularly missing from that is women. We need to have a really good representation of society in the people developing software so that it works for society in general. But I think the main thing is that we're trying to give our students a vision for what they might be able to do, about what could be done with digital technology, but also perhaps what shouldn't be done with digital technology. Now, if you're interested in the Computer Science Unplugged material I've shown you, it's on the website, and I'll give you the URL at the end, but I just want to point out also that we have developed versions that can be used at home, where you just need a parent and a child working together. And what we've done is, for each of these activities, we've provided a photo of a parent and step-by-step instructions on how to do those. So for example, this is that parity magic trick, but it's being done just using cardboard that's been cut off a cereal packet. So let's go back to what Bandura said. He was talking about complex technologies. Well, they are complex, but they can be understood. I mean, someone had to understand them to be able to develop them. And I hope that I've given a little bit of insight into how we can show even fairly young students how these technologies work so that they can understand them, and even better, that we enable them to be able to influence them, that we've even given them a vision that they could do something with this technology. I want to finish with a proverb from the Maori people of New Zealand. They arrived here long before my ancestors did, and they have a lot of wisdom that applies very well to the technology that we're talking about. And the proverb goes like this: He ata te mea nui ke tēnā ao, which means you ask me, what is the most important thing? Maku e ke atu, I'll tell you. And in fact, there are three things in this proverb that are the most important thing. Here's the first one, he tangata, which is people. The second one, he tangata, people. He tangata, people. And as we develop technology, as we use all of these tools, we need to be really focused on the idea that we're developing programs, devices, technology for people. Thank you for your time today. Here are the websites that I've been using. csunplugged.org is our main website with a lot of the unplugged activities on it. And then the CS Field Guide has a lot of activities that are more interactive. It's actually a bit of a textbook that explains some of the ideas. It's intended for slightly older students. But those are the resources that I've been using today. Thank you for your time, and I look forward to having discussions with you.
I'd like to thank Professor Tim Bell for his inspiring presentation and for accepting our invitation to be here with us at Ctrl-E 2020. Agradecemos a participação de todos vocês também que estiveram conosco assistindo essa apresentação. Confiram a programação completa do evento no nosso site ctrl-E.ci.fpb.br. Né? Lá consta o horário exato da interação síncrona com o nosso participante, com o Tim Bell e com outros participantes também. Acompanhem também, participem, interajam conosco e com outros participantes nas nossas redes sociais. Instagram, @congresso.ctrl-E e Facebook, @ctrl-E.br.